3.1, part 1. So really only 2 equations for this section. It's not up there? That's awesome. So really only 2 equations for this section. But I'm going to write down 3. One's just a kind of a different version of the other one. So our first equation is just going to be total force or net force is equal to mass times acceleration. So Ft is equal to...
Is that MA?
Yep. That's going to be measured in newtons. And then we have the different version of this that I was telling you about is force of gravity is equal to mass times the acceleration due to gravity. So that's really the same equation, just we replace it with a specific A. And for this section, we're going to say g is positive 9.8 meters per second squared. It'll just make our math a little easier and we won't have to have negatives that cancel out all the time. Our last equation is force of friction equals mu, which is the coefficient of friction, times the normal force. So, mu and that is unitless, because it's just a ratio between the force of friction and the normal force. And it's also always between 0 and 1. This one should be pretty straightforward. How much in newtons does a 50 kilogram bag of grass seed weigh? So we're going to say force of gravity just equals mg. So when we say weight, we're usually talking about the force of gravity. It's going to be 50.0 kilograms times 9.8 meters per second squared. And what do we get when we multiply those together? You guys can probably do this without your calculators. 490 newtons. Almost 500, that is correct. A 16 Newton force is applied to a 3 kilogram box. If the coefficient of friction is 0.25, what is the acceleration of the box? Right? So for a lot of these problems, what we're going to have to do is come up with kind of a total force equation and then substitute into that. So this is where it starts to get a little tricky. And I would suggest, even though you can probably do this one without like setting up this initial equation, do it anyway because the equations are going to get longer and more complicated later on. So what we're going to do is write down our total force and what forces are acting on the box. Gravity is acting on the box. What forces are affecting its motion, though, is really what I'm looking for. Friction and that 16 Newton force, the pushing force. Does that make sense? So the total force is going to be equal to the force you're pushing with minus the force of friction. Does that make sense to everybody? Everybody see how I came up with that equation? And if we drew the diagram, it'd look like this. So we've got our free body diagram would be, we'd have gravity pulling down, normal force pushing up, have some force pushing it that way that's probably bigger than the force of friction holding it back. Does that make sense? And the normal force and gravity are not going to be included because the box is going to be moving that way. So those are perpendicular and don't really have an effect, and they also cancel each other out totally. Does that make sense? Alright, so what does Ft equal from the equations we went over before? Mass times acceleration. Acceleration is what we're looking for. The pulling force is just going to be 16 newtons. Minus, what's our equation for force of friction? Mu Fn. I'm going to write this out kind of a long way this time. What is Fn going to be equal to based on the diagram we have over there? Fn is going to be equal to Fg. Does that make sense? So you can say ma equals 16 newtons minus mu Fg. And what does Fg equal? Mg. So force of gravity is equal to mass times acceleration due to gravity. So now I substitute in what we know. We say 3 kilograms times A, which is what we're looking for, equals 16 newtons minus mu is 0.25 times M is 3 times G is 9.8. And what do we get for A when we solve that? And what do we get for the acceleration? 2.88 meters per second squared. Right, any questions on that? So an elevator weighing 246,000 newtons is supported by a steel cable. What is the tension in the cable when the elevator is accelerated upward at a rate of 3.12 meters per second squared? Okay. So we draw a picture here. We have our elevator. And it's being pulled upward. And we've got force of gravity pointing down. So what is the total force in the elevator going to be equal to? Those two things. So the tension in the rope, we'll call that F tension. And if it's moving up, which are we going to make positive, do you think? That tension in the rope, right? So the total force in the elevator is going to be equal to the force of tension in the rope, and we're going to add or subtract the force of gravity. Subtract since it's pointing in the opposite direction. Does that initial equation make sense? Okay, so it's going to be ma equals F10 minus mg. Do we have the mass of the elevator?
Yes.
We have the weight of the elevator. So we're going to do this off to the side. Fg equals mg, so 24600 equals mass times 9.8. And I forgot a 0 there, didn't I? Yeah, I need to write that better. 24600. So first thing we're doing is finding the mass of the elevator, just because we're given the weight. It's easier to work with the mass. So what do we get for the mass of the elevator? Alright, so now I can start substituting things in. So we've got 25102 kilograms times 3.12 meters per second squared equals force of tension, which is what we're looking for, minus 25102 kilograms times 9.8 meters per second squared. And we solve for F tension, what do we get? Three, 2, 4, 3, 1, 7 newtons. So that's the tension in the rope. So that's how hard the rope is pulling up. So an example of something you'd have to solve for with that would be, you need to figure out how strong a cable you need to use in the elevator. You can use this equation to figure out what the tension of the rope would be at a certain acceleration. How would this equation change if it was going down instead of up? So if down, we'd say Ft is equal to, since it's going down, we'd say Fg minus F tension. Does that make sense to everybody? Alright, so this one you have to remember things from the last chapter. I know that's totally unreasonable of me, but it'll keep coming up. I know. The best way to learn is just to learn it once and then forget it forever, right? Yes. Alright, a 1,425 kilogram car is traveling at 12 meters per second, applies the brakes to stop over a distance of 47 meters. What is the minimum coefficient of friction required to stop the car? Yay. Okay. So first thing we're going to need to find here is the acceleration that the car underwent. So let's start with that. So we know VO is 12 meters per second. What's VF going to be?
0.
Yep. And we also know delta X equals 47 meters. All right. And then we have, and we're looking for A. All right. So what equation are we going to use? So you get 0 equals 12 squared plus 2a times 47. And what do we get for a when we solve for that? Negative 1.53 meters per second squared. Any questions on how we got that? Alright, so now we're going to use that in our FT equation. And what forces are acting on the car? Friction. Anything else? Gravity and normal force, but those cancel out. So all we're doing here is force of friction. Now there are a couple ways to approach this. We almost always subtract force of friction from whatever we're doing. So the car is going one way and friction is going the other way. So would you guys like to make friction negative? Yeah. Okay. So we'll just say equals negative friction. And then we can keep everything the way it is. Alright, so we've got MA equals mu, and so force of friction is mu times what? Fn, and Fn is equal to what since it's on a flat surface? So we've got our car. So force of gravity and normal force. So mu, Fn, I'll go through it again here. We get negative out in front there. So Ma equals negative mu, and Fn is the same thing as Fg. So it's equal to Fg, and Ma equals negative mu. Fg is different than G. And what happened? Does the mass of the car actually matter? No, mass cancels. So A equals negative mu G. So we get negative 1.53 meters per second squared equals negative mu times 9.8. And what do we get for mu? And there are no units on that, so that's just our answer for mu. Any questions on that one? There's no units. Mu is unitless. It's the Greek letter mu. So mu looks like this. If you're really drawing it rightly. It's like a funky U.
I was drawing a funky M.
Oh my gosh, I really wish that that word, are those right and you for all my M?
No.
Yeah.
No.
No, those are those are m, this is mu.